Hello everybody, welcome back to our class. This is the third lecture and today we're gonna talk about gates for digital circuits. Last lecture we talked about numbers and how can we represent numbers in digital circuits, and now we're gonna talk a little bit how we do operations with those representations, with those numbers, right? And most of those operations will be performed through gates. What are gates? Gates are simple digital circuits that takes one or more inputs and produce a binary output. And so it transforms the data into something based on an input. It performs an operation and provides an output. And because we are working with binary, n input gate has 2 to the power of n possible outputs, right? And the behavior of this gate can be described with a truth table of 2 to the power of n entries. We're gonna see in a bit. And usually the input output we read from left to the right and from top to the bottom. So usually the circuits that you're gonna see, the gates and the circuits as well, you read from left to the right. So these are the inputs and here is the output. And usually top bottom as well. It's easier to read that way because we're gonna have more complex digital circuits in the future. So input letters, usually we use the beginning of the alphabet and lowercase. And outputs, usually it's Y, or we can use out, or we can write the equation here. We can use several types of output, but usually it's Y. It's one is the most common output. And as I said before, we can represent the output of a gate using a truth table. So what's happening here? So we have the inputs, the n inputs, and we have 2 to the power of n. So 2 to the power of 2 is 4. So we have 4 possible inputs for this. When a is 0, b is 0. When a is 0, b is 1. Or when a is 1, b is 0. Or when a is 1, b is 1. And here, in this case, we have one output here and another output here. Because this is one gate and this is another gate. This is just one example. We're gonna see in a bit different types of gates. So the most simple gate that we can have is just like one input gate, right? We can, and the most basic gate that we have is the NOT gate, or the inverse, or the complement. Anything that switches the flips the inputs that you have. For example, if I have 0 here, the output's gonna be 1, and if I have 1 here, the output's gonna be 0. And we have several notations. So this first one here, it's A prime, for example. Sometimes you say A prime. Sometimes you can say not A or bar A. So it all depends on the notation. This one is more, so Verilog uses complement, like languages in general, they use not A in this way. When you write, usually we use bar on top of the input. So, and yeah, so this is the NOT gate. Another single output or single input or one input gate is the buffer gate. It's the same as the NOT gate, but it copies. So if it copies the input to the output. So if it's 0, the output is 0. If it's 1, the output is 1. Doesn't seem actually really useful, right? Because it's the same behavior of a wire. Like that makes right. So if I have this here and here, I don't need this guy. Otherwise, it's just a wire, and that's gonna work as the same. But if we are looking into the digital to digital level, that doesn't make any sense, right? To have this gate. But if you're saying the analog level, sometimes you need to reinforce or to to raise up the current that you have, to deliver the correct current from this point to this point. So this gate, the buffer gate, is more common in the analog level, but we're gonna see it in some cases as well. And it's just like a buffer, so it's just the boolean for the buffer is just A, so it's just the wires, the connection or the input that you have. So let's move on to the two input gates. Those are of course more interesting because we start to doing operations. Not that the buffer and the NOT is not useful, of course they are, but now we start to having operations. We start to modifying, to comparing our inputs to have a function in the end. And the first that I want to talk about is the AND. So for the AND gate, it's a comparison, right? So we're gonna see if both inputs are true, so my output is gonna be true or it's gonna be high. So you can see from the truth table, the behavior of this gate is if any of those inputs are 0 or false, my output is false. But if I have both inputs true, my output is true. So we have also several representations. We have like a dot, this dot representation. We also can just put it together. It's really common in equations if you're not having a problem with double meaning, or if it's really clear that this is it's an AND, you can just leave it together and we can understand that it's an AND operation here. And this is an intersection. It's really common to see this more for people that use sets and other types of calculations. It's not really common to see in other environments. For Verilog, it's usually we use the I forgot the name of this. Sorry, this AND here, right? This symbol, and when you're writing, you can use the dot notation or together. And the symbol is really important. So the symbol is this like D with the inputs to the left here, because we're gonna see this a lot in several demonstrations. So another input gate is the OR operation. So it's another Boolean operation, and it's true if one input is true or the other input is true. So we don't have to have both inputs true for our output to be true, right? And in this case, we can use the plus sign to describe the OR operation. And in Verilog, it's the straight bar, the vertical bar, and it's also common to see the union symbol here, but we're not gonna use that very much. So the behavior is described here. It's every time that our input, either of our inputs are true, our output is true. It's only false when both our inputs are false. We also have another interesting and really useful gate, that's the Nand Gate. The Nand Gate is basically the not AND, so you can see that the output of this gate is going to be the opposite of AND. When you have when I have both inputs true, the output is false, and it's true in whatever other option. And you can see that now we are putting together the NOT gate and the AND gate. Usually when you see the gate, I forgot to mention that the OR gate has this symbol here on the diagram that you're going to see. So it's a curved input and a pointing output. And so going back to the NAND gate, so the NAND gate is basically this guy here, right? Every time that you see a little circle like this, it means that there's a there's a NOT gate here. So any input that I have from this symbol, it's the complement, it's the NOT of it. We can have these small circles here in the inputs as well. sometimes you have just to simplify your diagram. So you know that before entering this symbol, the AND operation, sometimes you can have B, for example, here with a circle, and it's not B. It's the complement of B. Yeah, so in Verilog, you just put together like the NOT symbol and the AND symbol, and you can have the NAND gate. And when you're writing it, you kind of put it together as well. So you have the AND here, and you have the bar over the operation, so you can have the NAND operation. Over the AND operation, the bar is over, so you have the NAND operation. So we have the version of OR, so it's the NOR operation, it's the NOT OR. The behavior will be the opposite, the complement of OR. So if both inputs are false, my input is gonna be true. If any input is true, my output is gonna be false. In a similar way, we have the operation, and it's complemented by a bar on top. And in Verilog is the same, is similar to what we see, but the operation is the plus, so it's an OR operation. And that's interesting that we use bar here, but it's and with the NOT here, okay. And I remember that if you're using bar, you don't have to put parentheses, but that's, I think you're going to discuss this in the lab in the future. Yeah, okay. So the NOR gate again. So we have the complement. We have the complement, so we can see the circle again here in front of the symbol of the OR symbol. So this is a NOR operation. And now we're gonna talk about another two inputs, and that's really this gate is really important. It's the exclusive OR or XOR. It usually is indicated by this circle with a cross. I don't know if there's a specific name of this, but it's the exclusive OR symbol, and its behavior. It's always true. It's true if I have one. If I have one input's true, but not both. So what does it mean? It means that it's always it's true for an odd number of true inputs. Is that clear? So I'm going to repeat. So the exclusive OR is always true when we have one input true but not both. And what does it mean is that we have an odd number of is it true for an odd number of true inputs? Because in this case it's really easy to understand this way, right? Because it's only two inputs, but we can have more inputs. And let's say that we have 3 or 4 inputs for this gate in a different version. You can see that this is the behavior. The odd number of true inputs, it's always true. So this is the symbol for Verilog, and this is the symbol that we're using on equations. And the symbol for the circuit diagram is this, like this pointy OR, but with this extra line here, right, at the inputs. So this is the exclusive OR. And in the same way, we have the complement of the exclusive OR, the XNOR gate. And so the Boolean representation is A exclusive OR complemented, and we have the same here. So we have, for the exclusive OR we have this, for the complement, for the XNOR we have this guy, and the behavior you can see that's the opposite of the OR, of the exclusive OR, sorry. And the symbol is the same, but with the circle here that represents the complement. Okay. So as we expect, we can have more than 2 input gates, except for the NOT, of course, because we're like, for the NOT it's single input, but for the other gates we're gonna have more than one input sometimes. So As I said before, we have 3 inputs here, so we can have 2 to the power of 3 possible outputs, and that's represented here on the table. So we have A, B, and C, and all the possibilities, all the 8 possibilities for A, B, and C. All zeros, C is 1, only B is 1, B and C is 1, only A is 1, A and C is 1, it's true, A and B is true, A, B, and C is true. And in this case, as we said before, we only have true, we only have 1 or 2 on the output of an AND gate if all the inputs are true. So AND, this is the behavior of the AND. And so we can expect the same behavior that we have for 2 inputs for the higher level inputs, like for a higher number of inputs. As I said before, the exclusive OR is a little less intuitive because some people will explain to you that it's just like it's true if one of the inputs is true, but it's false if both inputs are false. But when you have 3 inputs, that's not true, right? We have all the inputs true here, and it's true. Can you see? So in this case, it's because every time that we have an odd number of true inputs, it's false. So in this case, we have 2. Oh, sorry. Every time that we have an even number of outputs, true inputs, our output is false. So in this case we have 2, that's false. In this case we have 2, so it's false. In this case we have 2, that's false. And in this case we have 3, so in this case it's true. So the exclusive OR is really important because we're gonna build a arithmetic and logic unit. We can do really interesting operations with the exclusive OR. That's why it's important. Oh yeah, so how can we build this 3 input gates? If you can have really specific and really big complex CMOS. We're gonna see CMOS in the next lecture, but you can build them using really complex. Not really complex, but more complex than we have for 2 gates. But why don't we just like put together 2 input gates, and we have 3 input gates? That's gonna work as well. So instead of building a super complex 3 input gate, right, like this one, we just use like simple 2 input gates to build our 3 input behavior that we want. So you can see that what we are doing, it's like parentheses are not actually necessary to represent this equation, but what we are doing here is just like we're evaluating A or B, and with the result of this we're evaluating the result or C, and we have our 3 input OR. And that can be done with any type of gate, right? To have a larger level of inputs. And we start to see that we can put them together, right? We can have those gates and like one following the other in a sequential order, and that's gonna provide us with an equation. So that's what I'm saying. So if I need 8, in this case is 1, 2, 3, 4, 5, 6, 7, 8 input or input, I can build like with simple OR gates, and that's gonna represent the same behavior that I want, the exact behavior that I want with OR input, with 8 input OR. So we can see that we can use the gates in a clever way to achieve different types of behavior that we want, right? For example, if I don't have a NOT gate and for some reason I have an IC or integrated circuit that has, for example, an OR gate or a NAND gate, I can build a NOT gate with it. It's just plug the same input twice on both inputs of the gate, and I can have the behavior. because you can see that this is 0 and 0, and the output of the OR would be 0, right? And it's complemented, so it's 1. And in the same way, so it's 1 1 because it's the same wire. If it's OR, would be 1, but the complement of this, it will be 0. So you have this behavior of the NOT, of the complement. In the same way you can do with the NAND gate. So usually that's when you're developing and synthesizing like FPGAs or devices like that, that's not really common. But when you're prototyping, it's possible that you can face this type of decisions, that you have an IC that only have NAND gates. That's really common, and you have to develop your circuit around that. So you can build an exclusive OR gate using NAND gates, and so here you can see that we have an OR gate. We have two AND gates, and we have the complement of the bits here, right? The complement of A here and the complement of B here, and you always look for these connections. So in this diagram is not really good, but this wire here is not connected here. So this wire here goes directly to this input here on the AND gate. So this circle here, it means that this connection it's actually connected to this, but because we are missing a circle here, it's not connected. But this one is connected. It's just because it's really close. So, and this is one example on how you can solve some diagrams and understand what's happening here. So you have your inputs A and B. You can have 2 to the power of 2 possible inputs. So this is your input side, and let's decide what's happening here. So it's complement of A and B. So and right? So it's 0 and 1 in this case. So it's 0 because it's an AND gate. In this case, the only true is gonna be here because this input it's gonna be 1, and 1 and 1 it's gonna be 1 for the AND gate, and the opposite as well. And so, and when you're evaluating this guy, we only look at this. So we're gonna have 0 and 0, or 0 or 0 is 0, 1 or 0 is 1, 0 or 1 is 1, 0 or 0 is 0. So you can have the behavior of exclusive OR using AND and OR gates and complement, right, in the NOT gate as well. We're gonna see in the unit 2 more in details the combinational logic and Boolean equations and stuff like that. So there's a law that if you're having, in summary, you can. It's one way to simplify some equations. When you have like an A and B, for example, in this way, if you have this operation, for example, and it's complemented, it means that it's the complement of the first one with the, for example, this is AND operation, right? If I have a complement over this operation here, it means that I have complement of the first one, A, or the complement of the second one. We're gonna see that in more detail in the unit 2, but you can see that I also can build simpler versions of the AND gate, for example, using because sometimes maybe I don't have an AND gate and I can build with an exclusive OR. Oh, sorry, with an OR gate and some NOT gates. And I know that's for sure. I can, of course, that I can build the behavior table here and make sure that it's an AND, but I'm sure that this is an AND because of the Morgan's law, because I have OR, it's the complement of OR, and it's in my inputs are complemented as well. So these gates here give me the behavior of an AND gate. Yeah, so in the next, in the following, I think next lecture will be about CMOS. But unit 2, we're gonna talk about conventional gates. You can see that you can interconnect the gates. You can have like this interconnections to build different functions, and in this case we only see like building different types of gates, some examples, but we can build big functions, and we can have more than one input because it's gonna be larger and more complex. But the basic unit of our combinational circuits are gates and interconnected. And we're gonna see that the output at a given time is a function of the inputs at that given time as well. And we're gonna see that in unit 2. Okay, so see you soon. Take care.